Assalamualaikum and hi everyone. Before we begin our presentation, I would like to introduce our team members. Each of us play a vital role in preparing our reports, and I'm excited to share our findings. First, we have Amir Razi bin Azmi. Next is Ni Haziq Hazimi bin Ni Ahmad Maiza, and I am Intan Azina binti Jamaluddin. Finally, we have Davana, anak lelaki S. Ravindran. Together, we have collaborated closely to bring you this presentation. Each of us have leveraged our strength, work diligently to ensure that our project is comprehensive and well done. Firstly, let's take you through the table of contents of our reports. This will give you a clear overview of what to expect and help you to navigate through the section more efficiently. We will start with introduction. This chapter set the stage for what's to come, providing background information and outlining the main objective and scope of the reports. For the introduction is, filters are electrical circuits that allow certain frequency components to pass while rejecting others. They are used to reduce unwanted frequencies, frequency noise caused by the background noise, or non-linearity of certain components. Filter can block high pitches, not be transmitted effectively, remove high frequency that sharpen and improve edge. There are 4 types of filters: low pass filters, high pass filters, band pass filters, and notch. Notch is the band reject or band stop filters. Filter also can be passive or active. This assignment requires the development and simulation of a 4-order bandpass active filter using an operational amplifier. Active filters are generally operational amplifier circuits that use resistors and capacitors to provide the desired frequency response. Bandpass filters only allow a certain frequency band pass through them, mostly between the cut-off frequency. And finally, the filter's gain is the highest at the resonant or center frequency, that known as total passband gain. Next, I will explain about the theory of this report, which is a fundamental concept in 4-order bandpass filter. Understanding this theory is crucial for grasping the underlying principle that drive much of the research and practice in this area. For the theory is, a 4 bandpass filters is a circuit that combines a 4-order high-pass filter with a 4-order low-pass filters as a discriminating filter, allowing transmission of a specific frequency spectrum. The passband is governed by cut-off frequencies FL and FH. FL representing minimum frequency and FH representing the maximum frequency. The center frequency FC is known as the resonant frequency or peak frequency. The high-pass filter gets signal with frequency below the cut-off frequency, while the low-pass filters isolate and extract signal with higher frequency. As you can see, Figure 1 shows the slope of the frequency response, and for the Figure 2 is the stage of order and slopes, and lastly, for Figure 3 is frequency response of bandpass filter. That's all from me. Thank you.
Hello, my name is Ni Haziq Hazimi bin Ahmad Maiza. My matrix number is DE220160, and for this part of presentation, I will continue on simulation on the circuit that our group have made using the simulation software, Proteus Lab Center software. So first, before I continue to run this simulation for you, I will explain in details about what we modify to the operational amplifier, as you can see on your screen right now. So first, we use this 5.3 kilo ohm resistors and 0.1 microfarad capacitors because our group number 2, we set the low frequency at 300 Hz as well as the high frequency at 2 kHz. So this first operational amplifier as well as the second operational amplifier is actually the high pass filter part of the band pass filter. So this both amplifier is second order high pass filter. And then this capacitor, two capacitor that have one in between capacitor is the resistors, as well as this resistor here connected to ground, and the output pin number 6 connected to RF and R1 in series, and the middle of those two resistors will connect to pin number 2, which is the limiting pin. So why we need this? Why we need these resistors to go into the pin number 2? So I will explain in the general theory. So the negative feedback stabilizes the gain and frequency response of the amplifier. It forces the operational amplifier to balance its input, maintaining a virtual ground at the inverting input, and thereby controls the output precisely according to the desired transfer function. So there you go. That's why we use these two resistors connected to the pin number 2. And the rest we just ground it, so to make the circuits complete. So these two operational amplifier, as I mentioned before, will use the exactly same values for the capacitors and resistors. But for the low pass filter, we use 10 nanofarad in capacitors and 7.95 kilo ohm in resistors. Same as the high pass filter, this low pass section also use the same values for both of its low pass filter, which is 10 nanofarad and 7.95 kilo ohms. So I will now proceed to demonstrate the output graph to you. So the frequency response stated that we have 17.1 decibels in mid gain. This is far less from our targeted mid gain because we intend to get 39.55 decibels or some point between them. This 17.1 in decibel is far less to reach our target. So what do? We put operational amplifier to act as amplifier to amplify the gain. So this is the amplifier that we use to amplify our gain to 39.55 decibels or somewhere near them. So notice that when I run this simulation, our frequency response is now at 39.4 decibels for the mid gain. So this is actually nearer to our targeted value, which is at 39.55 decibels. So what we have to do here, we have to locate where is the low pass frequency and where is the high pass frequency. So 39.4, we must subtract 3 decibels from it so that we get both low pass and high pass. So 39.4 subtract 3, we took out 3 from it, we got 36.4, right? So we move our cursor to the 36.4, as you can see on your bottom right of the screen, and at bottom left of the screen we get 299 Hz, which is good because we intend to get 300 Hz on the low pass frequency. What about the high pass frequency? Same, we move the cursors to 36.4 and we get 2.05 kHz in high pass frequency, which is quite good since we intend to get 2 kHz. So there you go. This is the simulation part of the assignment. So I think I explained enough for you to understand, and thank you for watching. Assalamualaikum and goodbye.
Okay, Assalamualaikum. My name is Amir Amili Razik bin Azmel. My metric number is CE22002. My part is result and analysis in laboratory measurement. So firstly, we did this experiment for the circuit we designed in Proteus. We set our input voltage to 1 volt and input frequency is 1 kHz and connect it series with a capacitor as the input of the circuit. We also set the voltage from the supply to 15 volt and connect the supply to the pin 4 and pin 7 of the op-amp as a positive VCC and negative VCC of the circuit. We also connect the jumper wire on pin 6 on the VCC as the output of the circuit. Okay, first, this is a figure circuit which is connect with a power supply, function generator and oscilloscope. Okay, next, when we start to test the output of our circuit, we connect the channel 1 to the input of our circuit and connect the channel 2 to the output of our circuit with the probe. By using the input voltage around a 1.01 volt and a frequency around a 1 kHz, we get the result around 24.9 volt for a peak to peak. So the peak is 12.45 volt as our output voltage for our circuit. If we use a formula of the gain A equal to V in over V out, we get our gain is 24.95, which is around. So for a mid gain A dB, we use a formula 20 log A, so we get the answer 27.85 dB. Similar with my simulation result. Okay, lastly, this is our result graph from a laboratory measurement. This is our result graph from a laboratory measurement. Quick similar with our simulation measurement because we use our frequency between 0 Hz to 2.6 kHz. Based on the theory and calculations, we'll get mid gain around 27.84 dB. If we make our output frequency higher than 1K, we observe that our output voltage decrease because the gain is decreasing at a frequency response graph. When the input frequency is over than 2.6 kHz, which is the high cut-off frequency. When the frequency is less than 180 Hz, we can observe that the output is increasing if we increase the input frequency from 0 to 180 because the gain will be increased when the input frequency is increased from 0 to 180 Hz.
My name is Devana Analakirandan and my matrix number is CE220129. And today, I would like to conclude this presentation for our project. So, in conclusion, we as members get to know that filter is an electric circuit that allows some frequency components and reject other unwanted elements too. And our project here is to focus on pass filter based on OPM 741. So that's our primary objective. And we have get to conduct the experiment to find the mid gain, bandwidth, high pass and low pass value, and find the FL and FH values by doing the laboratory experiments and by simulation from Proteus. And then and we get to demonstrate the design filter perform, testing measures and simulation data given from the lab circuit that we did. and finally the project was successful in constructing and designing the fourth order bandpass filter using the OPM 741. And this project advanced our understanding of and ability to use filters in electronic circuits. So that's all for me. Thank you.